After months of ongoing issues and multiple delays, Boeing made the decision to bring the Starliner back to Earth without the astronauts on board, and they did just that. The spacecraft landed safely, and at first glance everything appeared to have gone smoothly. Many people even congratulated Boeing, with some suggesting that they could have successfully returned the astronauts with Starliner. But we were wrong. Despite the seemingly flawless landing, it became clear there were serious problems during the return mission. Multiple thruster failures, navigation system glitches, and overheating occurred, casting doubt on whether the spacecraft is truly ready for crewed missions. While the capsule managed to land successfully at White Sands, New Mexico, NASA's decision not to carry astronauts aboard due to the risks turned out to be wise. One of the main problems during Starliner return was the overheating of its thrusters, which poses a significant risk, especially if astronauts were aboard. The overheating occurred because the design of the doghouse, a compartment that holds the thrusters, traps heat, acting like a thermal insulator. This caused higher than expected temperatures, which in turn led to thruster malfunctions during the re-entry. Some of the thrusters failed, and while the spacecraft was able to compensate using backup thrusters, this wouldn't be ideal with humans on board. If astronauts were inside, the overheating could be life-threatening. Thrusters are critical for the deorbit burner maneuver that ensures the spacecraft re-enters the atmosphere at the right angle. If the thrusters malfunction during this phase, the spacecraft could lose control, leading to a dangerous descent. Additionally, overheating could damage internal components, or even raise temperatures inside the capsule, making the environment unsafe for the crew. NASA engineers noted that during tests, some thrusters experienced temperatures so high that Teflon seals expanded, blocking propellant flow and reducing thrust power. Typically, these seals are designed to work under precise conditions, and once temperatures rise above safe levels, likely around 200 C or higher, their performance becomes unpredictable. Even during the return mission, several thrusters underperformed due to this overheating issue, prompting NASA to focus on resolving this for future flights. The complications didn't stop there. Earlier in the mission, helium leaks were detected, and they had already raised concerns among NASA officials about the overall performance of Starliner. Fortunately, engineers managed to stabilize the system, though it remains a point of investigation. Despite these issues, NASA and Boeing have expressed confidence in Starliner potential, but the road ahead is challenging. The spacecraft has been delayed multiple times due to similar problems, and NASA is closely evaluating whether Starliner is ready for a crewed mission. Currently, they are debating whether to proceed with a manned mission, Starliner 1, or conduct further test flights. Looking forward, Boeing is committed to fixing these issues, especially the thrusters and helium leaks. They are working on upgrades that may improve the reliability of future missions, but these fixes will take time. NASA has already delayed the first official crewed mission, originally scheduled for 2024. In the bigger picture, this series of technical failures highlights the ongoing challenges that Boeing faces with the Starliner program. Boeing has already incurred significant costs, with losses exceeding $1.6 billion, and some analysts are even speculating about the company's long-term involvement in manned space flight. However, NASA continues to support Boeing as they work through these challenges with the hope of certifying Starliner for future missions. Meanwhile, SpaceX continued to push the limits. Their latest milestone might seem like something out of a science fiction movie. They managed to launch 2 rockets back-to-back within a single hour. This feat is especially impressive considering the typical space launch, which usually involves extensive preparations with hundreds of engineers working for months or even years. The back-to-back launches were also a response to the recent FAA grounding of the Falcon 9 rocket. The FAA had temporarily halted Falcon 9 launches following a landing mishap on August 28, where a booster failed during a powered landing attempt and was destroyed after tipping over on the drone ship, a shortfall of gravitas. This incident was the first unsuccessful landing since 2021, breaking a streak of 267 successful landings. The FAA required an investigation into the incident, but allowed launches to resume shortly after, provided that SpaceX met all licensing requirements. Despite this setback, the FAA allowed launches to resume after a swift safety review confirming the incident posed no threat to public safety. The first of the recent back-to-back launches took off from Cape Canaveral Space Force Station, carrying 21 Starlink satellites into orbit. This was closely followed by another launch from Vandenberg Space Force Base in California, which also deployed 21 satellites, including several with direct-to-cell capabilities. A key highlight of these missions was the booster used in the California launch, which marked its 9th successful flight and landing. This particular booster, known as B-1058, has had an illustrious career supporting a variety of missions, including multiple Starlink deployments and rideshare Missions involving both commercial and classified payloads on its 14th flight B-1058 made history by becoming the first booster to be recovered 14 times, underscoring SpaceX's advancements in booster reusability. This is not their only achievement. In 2024, SpaceX has been stepping up their game in many areas. By mid, SpaceX had conducted a total of 87 launches, which included 84 Falcon 9 missions, 1 Falcon Heavy mission, and 2 Starship test flights. This brought their launch frequency to an impressive average of 1 launch every 2.8 days, maintaining a success rate of 98.8%. SpaceX's Starship program also saw significant advancements, with multiple test flights aimed at refining and demonstrating capabilities crucial for future deep space missions. The 4th test flight of Starship marked a milestone by achieving the first soft splashdown, showcasing the potential for reusable space travel beyond Earth orbit. The company is gearing up for a robust schedule that aligns with Musk's long-term vision of launching 1,000 rockets per year. On September 7, 2024, Musk revealed on Twitter that SpaceX is set to launch its first uncrewed Starship missions to Mars in 2 years. This mission is scheduled to align with the next Earth-Mars transfer window, expected to occur around 2026. The primary objective of these uncrewed missions is to test the reliability of Starship landings on the Mars surface, which is a critical step toward achieving human exploration of the Red Planet. If these initial tests succeed, Musk plans to launch the first crewed missions just 2 years later, by 2028. However, achieving these milestones requires not only advanced spacecraft, but also numerous preparatory launches to support these Mars missions. SpaceX will rely heavily on multiple variants of Starship, including a dedicated tanker variant designed specifically for in-orbit refueling. For every crewed mission, several tanker launches will be necessary to transfer fuel in space, allowing Starship to reach Mars and return to Earth. The exact number of tanker launches is still under debate, but estimates suggest that each crewed mission may require as many as 8 to 14 refueling. One of the most revolutionary ideas SpaceX has introduced to the space industry is catching rockets midair. This is one of the hardest achievements in the history of spaceflight, and SpaceX has managed to do it in less than a decade of Starship development. However, this method is still in the testing phase, and there are problems that need to be solved before it becomes fully operational. It could take dozens of more tests to refine the process completely. But what if there is a better way to recover both the booster and the upper stage? SpaceX has now come up with a simpler and more reliable method for reusing Starship and Super Heavy. In today's video, we'll explore this new approach. Before we dive deeper, make sure to subscribe to our channel for future updates on Starship and SpaceX's groundbreaking achievements. Mechazilla works by using giant mechanical arms attached to the launch tower. These arms are designed to precisely catch the returning booster as it descends from space. The advantage of this approach is that it eliminates the need for traditional landing legs, making the booster lighter and allowing for more fuel or payload capacity. Instead of landing on a drone ship or a landing pad, the booster comes down vertically and is guided into the arms of Mechazilla, which then locks it in place. Once secured, the booster can be quickly reattached to another Starship upper stage and prepared for the next launch. While this system has many benefits, it also presents several challenges. First, the booster is traveling at extremely high speeds. When it re-enters the atmosphere, it must precisely align itself with Mechazilla arms at just the right moment, or the catch will fail. This requires incredibly precise control and coordination between the rocket's navigation system and the tower's catching mechanism. Even the smallest miscalculation in timing, wind conditions, or alignment could cause the boost bore to miss the arms and crash. Another major challenge is the immense force involved in the landing process. When the booster is descending, it still carries a lot of kinetic energy which must be absorbed when it is caught. The arms must be strong enough to withstand these forces without breaking, while also being flexible enough to provide a soft catch that does not damage the booster itself. If the forces are too great, the booster or the catching mechanism could suffer structural damage. Additionally, winds or turbulence in the atmosphere can make it difficult for the booster to align with the catching arms. Unlike landing legs, which allow for some flexibility in landing location, Mechazilla requires extreme precision in a fixed position. If the weather conditions are unfavorable, the rocket may not be able to land at all. Another limitation of relying solely on Mechazilla is that it is only available at a fixed launch site. This means that SpaceX can only land boosters in locations where a Mechazilla tower is installed. While this is fine for reusable launches from a single location, it becomes a problem for missions that require recovery in different locations, such as those launching from floating platforms or other spaceports. Because of these challenges, SpaceX has been looking into an alternative recovery method that does not rely entirely on Mechazilla. Instead of catching the booster midair, they are now considering a more traditional approach, landing Starship and Super Heavy on large floating drone ships at sea. This method has already been Used successfully with Falcon 9 rockets, which regularly land on autonomous drone ships after completing their missions. By adapting this method for Starship and Super Heavy, SpaceX can eliminate some of the risks associated with Mechazilla. Instead of requiring extreme precision to be caught midair, the booster would land on a stable surface, allowing for a safer and more controlled descent. The floating drone ships could also be positioned anywhere in the ocean, giving SpaceX more flexibility in recovery locations. Landing Starship and Super Heavy on a drone ship is far more difficult than landing Falcon 9, primarily due to differences in size, weight, engine power, and landing requirements. Falcon 9 and Starship are two completely different classes of rockets, and while the drone ship landing method has worked successfully for Falcon 9, scaling it up for Starship will require significant modifications. First, Falcon 9 is 70 m tall and has a diameter of 3.7 m, making it a relatively slim rocket. It weighs around 1.2 million pounds when fully fueled. On the other hand, Starship, when fully stacked with its Super Heavy booster, stands at 120 m with a diameter of 9 m. The combined weight of the Starship system is nearly 11 million lb when fully fueled, almost 10 times heavier than Falcon 9. Because of this massive difference in size and weight, the forces involved in landing are much higher. For Starship, when Falcon 9 lands, it performs a controlled descent using its Merlin engines, which each produce 190,000 pounds of thrust. A Falcon 9 first stage has 9 Merlin engines, bringing the total thrust at full power to 1.7 million pounds of thrust. This is manageable for the drone ships currently in use, as they have been designed to absorb this level of force. Starship's Super Heavy booster, however, is powered by 33 Raptor engines, each producing 520,000 pounds of thrust. This means that at full power, the Super Heavy booster generates nearly 17 million pounds of thrust, more than 10 times the thrust of a Falcon 9 first stage. The sheer amount of energy involved means that the landing platform must be reinforced to withstand significantly higher forces than what Falcon 9 requires. If a standard Falcon 9 drone ship were used for Starship, the landing would likely destroy the platform due to the excessive thrust and weight. Another major challenge is the heat produced by the engines. The Merlin engines on Falcon 9 use kerosene and liquid oxygen as propellants, which burn at a relatively lower temperature compared to Starship's methane and liquid oxygen-powered Raptor's engines. The Raptor engines burn at much higher efficiency in temperatures, meaning the drone ship's surface must be protected from extreme heat. The Falcon 9 drone ships currently use heat-resistant materials and water deluge systems to reduce surface damage, but for Starship, a much more advanced cooling system would be required to prevent the ship from melting or catching fire due to the high-intensity exhaust. Additionally, the landing process for Starship is more complex. Falcon 9 typically performs a single-engine landing burn, slowing down gradually before touching down on the drone ship. Its legs extend outward to stabilize the rocket upon landing. Since the Falcon 9 booster is relatively small, the risk of tipping over is minimal, and the Octograbber robot can quickly move in to secure the booster. In contrast, Super Heavy must use multiple Raptor engines for landing, and its greater height and weight mean that it has a higher center of gravity, making it far more difficult to stabilize on a floating platform. A larger, stronger securing